Welcome back, everyone, to a new semester. I hope you guys enjoyed the couple days off that you got. So today we're going to be starting our Similarity unit. Okay. So this is just a little bit of an introduction, and yes, caution, there are some movie spoilers ahead. Okay. First thing that we want to talk about is a warm-up. Okay. So before we can really get into understanding any of the topics of similarity, the first thing we want to do is kind of set up proportions. So in 2018, Buster Posey had 398 at-bats for the San Francisco Giants. Go Giants. But out of those at-bats, he managed 113 hits. Find his batting average for the 2018 season. Okay, so what batting average is, it's a comparison between what a player hits to the number of at-bats that they have. Okay, and so how we calculate this, right, is we use a ratio. Okay, and it's the ratio between the total number of hits and the total of number of at-bats. So we can use two different representations to kind of denote this. We can either say 113 to 398, so his total number of hits to his number of at-bats, or we can use it as a division symbol, which is 113 over 398, and either one of them will equate out to about 284, which, if you know anything about baseball, not a great season for him. Okay. So that's just kind of what we can use ratios for, okay? So next thing that we want to talk about, okay, let's extend the ratios. So let's just say we have a triangle right here, and we have the angle measures. We have 3x here, 4x here, and 5x here, okay? And you're probably going, what does that really mean? So when we're looking at these ratios, right, and that's kind of what that x value represents when we have variables inside of angles and stuff like that, is what we're saying here is that the ratio between the angles is 3x to 4x to 5x. And we want to find the measure of each angle. Well, how do we do that? All right. So one thing that we know is that the sum of the interior angle measures is 180 degrees, and that's by the triangle interior sum theorem, and triangle interior angle sum theorem. So we can relate that, and we know that, hey, if I take 3x, 4x, and 5x, all right, if I add those all up, that'll give me 180 degrees, okay? Which, again, simplifying gives me 12x is equal to 180, which means x is equal to 15. So now how do we figure out what the angles are? We substitute it back in for x, okay? So if I substitute 3 in for 3x, I get 45. 4x, I get 60. And 5x, I get 75. So when we solve for x, right, we have to keep the ratios the same. So the question is, does 3x to 4x to 5x, is that the same thing as 45 to 60 to 75? And the answer is yes, okay, because they all have a common factor. If I divide them all by 15, that gives me 3 to 4 to 5. And that's kind of the idea behind how these extended ratios really work. Okay, so now the reason that I have this image here is I kind of want you to just look at this for a minute and just kind of think about all the different shapes you see in here. Okay, we see some rectangles here. Right, we see quite a few rectangles. We also see some triangles, and we see different types of triangles, and we see larger triangles and larger triangles and larger triangles. And so we see a myriad of different shapes in here. And so the question that we want to just look at is, are any of these actually congruent? And the truth is there might be a couple of triangles in here that are congruent for various reasons. But if I'm looking at, for example, the rectangles, we know that they're not all congruent, right? But they're relatively the same shape, not necessarily the same size, okay? And that's kind of the idea between similarity, okay? And so we look at another image, and we can see a lot of the similarity being put to use in here, because it looks like we're walking down a hall, right? And it looks like if you were walking, right, these images, for example, the pieces on the ground, right, your brain is telling you that, hey, these are all the exact same size and shape if I was walking down the hall. And that's kind of how perspective drawing works, is it actually uses similarity in order to create an illusion that all of these are the same shape and size. But when you just look at them on paper, you can clearly tell that they're not the same shape and size. Same shape maybe, but not necessarily the same size. Same thing with these trapezoids over here, right? Same thing with these little arcs, right? They look like they have the exact same shape, right? But they're not at all the same size, even though if you were walking down this hall, they might look like that to you. And again, that's kind of how perspective works. And we see it everywhere, For example, this is for those of you that, and I'm going to apologize for those of you that are fans of the Harry Potter movies. Right, this is Hogwarts, and you can see, right, that this grand, huge thing that when you're putting it up on the screen looks massive and just looks like it takes up so much land and so much space, actually fits inside an entire studio. So it's that illusion, that perspective, that similarity, right, that kind of creates that that effect. Okay? The same thing works if you ever watch the movie Ghostbusters from the 1980s. Right? This is the Stay Puft Marshmallow Man, and in the movie he's the size of the Chrysler Building, or I think that's the building, or the Empire State Building, whichever one it is. It's about that same size. Right? But in reality, he's no bigger than a normal person. What the illusion comes from the fact that we've got all these cars that we're gonna basically make similar to what real car sizes are. Same thing with the trees and the roads and the everything else that kind of goes on. Right? They have the exact same shape, but definitely not the same size. And so that's kind of what we're going to learn with similarity, is we're going to learn how to create that kind of illusion, essentially, with creating something that's the exact same shape, but not the same size. Right, here we have, if you're fans of the Lord of the Rings, right, this is Minas Tirith, the White City, so to speak, right, where some of the bigger battles in that series kind of takes place. And so you can see here that it looks huge and massive, and it takes up a whole mountainside, right, in the movie, but in reality, I mean, look how tall these people are compared to it. Okay, and then if you were a fan of the movie Inception, this is actually the final battle scene, essentially, in the snow. Right, this is the giant building that they were trying to break into for the vault and stuff. Okay, so you can see that scales and similarity actually play a huge role, especially in the movie industry for visual effects. Okay, and then of course, Star Wars fans, I hate to ruin this. Here's George Lucas standing by all of his models that he used for the props in the original trilogy. You can see the Death Star up here, which is obviously not very big. Here's the Millennium Falcon, a very, very popular piece that clearly, R2-D2 is as big as, right? So you can see all these little things. Here's little Yoda, like all these little things in here that look huge on screen or look massive on screen are really not all that big. And again, similarity plays a role into that. Okay, so what does it mean for two shapes to be similar? Okay, so we have the definition of similar polygons, right? And we're gonna look at a more simple case. We're not gonna look at how to build, huge sets or anything like that for moves. What we're gonna look at is just, okay, how does this idea work? So we're gonna examine that using just polygons, and more specifically, we'll go with triangles at first. Okay, so definition of similar polygons is two or more polygons are similar if and only if, remember that's what the IFF stands for, their corresponding angles are congruent and their corresponding side lengths are proportional. Well, what does that mean, that word proportional? You heard it thrown around a lot of times. So what a proportion is, so if I look at, for example, let's just kind of take a second before we actually go into this example. If I look at this long chain here, right, each one of these pieces is called a ratio. Okay, the CD over YZ is a ratio. DA over ZW is a ratio. What makes anything in proportion is I'm saying, hey, AB over WX is equal to BC. So this piece right here, just this piece alone, would be considered a proportion. Okay? And the same thing I can say with this piece. Right? This whole thing's a proportion. And this piece is a proportion. So basically, a proportion is saying two ratios are equivalent. Okay? And so what the definition of a similar polygon says is, hey, I've got angle A here. All right, it's got to be congruent to another angle in here. Let's just say it's congruent to W. B would be congruent to X. C would be congruent to Y. And D would be congruent to Z. So if all four of those angles are congruent, right, we know that we possibly have similar sizes and shapes. But again, right, if one angle was longer than, or if one side was longer than another, we could still technically have or maybe these two were longer, we could still technically have the exact same angles, but not necessarily the same size. So the last thing that we need is we need to have all of their sides proportional. And that means that the ratio, for example, these all belong to the top, right? These all belong to the top. Right, or these all belong to the left-hand side, sorry. All the top belong to the left-hand side polygon, and all the bottom belong to the right-hand side polygon. polygon. So it doesn't matter which one we do, which ones are on top, as long as we keep it consistent. So if I put a side length AB here, right, and if I look at the ratio between AB and WX, it's going to be the same as the ratio between BC and XY, and so on and so forth for every single side. And that's what it means to be proportional. So if all those angles are congruent and all those sides are proportional, right, then we can say that the quadrilateral ABCD is similar, and that's what that little tilde means. It means it's similar to WXYZ. Okay, and that's kind of how similar polygons work. So here we have an example of triangle FGH is similar to triangle JKL, and I apologize for the shapes being all wacky. Right? List all pairs of congruent angles and write a proportion that relates to given sides. Okay? So again, this is where similarity, like the similarity statements and stuff like that, come into play. Just like congruence, remember that when we looked at congruence, F needed to correspond with J, G corresponded with K, and H corresponded with L. The same exact thing is going to work in similarity, which means that if I'm thinking about angles, all right, which angle has got to be congruent to angle F? It's got to be J. Okay? And so we can say that angle F is congruent to J, G with K, and H with L. But more so, right, if I kind of, I don't know if I can go backwards. Yeah, if I go backwards, all right, we can also see that FG then must correspond with side JK. Now, if these were congruent, we would say they're congruent, but what we have to say is that what we're going to look at is instead, because we're talking about proportions, which is equal ratios, the ratio between FG and JK has got to equal the ratio between any other two sets of sides. Okay, so FG to JK has got to equal the ratio between GH and KL, right? KL, and which has to equal the ratio between HF and LJ. So lots of stipulations for dealing with similarity. Okay, so in here we're going to determine if the two triangles are similar. If so, write the similarity statement. Okay, and so what we're going to look at is we're going to compare all the different sides and angles and stuff. And hopefully you can see that, well, this angle is congruent to itself, which is in this big triangle, right? And it's also in this little triangle, okay? So right now we know that these two angles are congruent, but we also know that this angle F is congruent to angle IWN, right? And angle C is congruent to WNI, right? Because these two lines are parallel here, so we have corresponding angles. Okay, so right now we know that all the angles are congruent, but we need, in order for us to actually prove that these guys are similar, we need to have the ratios congruent, or not ratios congruent. We need to have the ratios between the sides equal. And right now you're probably going, well, they're not, because 8 to 4 is 2 to 1, 6 to 3, 2 to 1, but 4 to 6 doesn't really work. However, remember, we're talking about the whole side length. So we're not comparing 6 to 3, we're comparing 6 to 9. And we're comparing 8, not comparing 8 to 4, we're comparing 8 to 12. Okay? And does that equal the ratio between 4 and 6? And hopefully you can kind of see that. So, I wrote alternate interior angle. Oh, bad, Mr. Kiefer. Bad, Mr. Kiefer. These are not alternate interior angles at all. Ignore this. Ignore this. Right? These are corresponding. That's by corresponding. Anyway, so when we check in the sides, right, we know WI, where we need to check, does WI, is it proportional, or sorry, the ratio between WI and FI, is it proportional to the ratio between IN and IC? And is that proportional to WN to CF, or FC? Well, WI is 6, FI is actually 9, 8 to 12, 4 to 6. And since they all simplify to 2/3, right, we have the angles are all congruent, the sides are all proportional. We can now say that triangle WIN is similar to triangle FIC. Okay? Now that magic 2/3 number, so they all, the proportion equaled the exact same thing, right? This is what we call the scale factor, okay? So what the scale factor is, it's the ratio of the lengths of the corresponding side lengths in two similar figures. So for example, if we want to find the scale factor between these two, if we already know that they're similar, right, what we might do is we might say, hey, BC is the side that we know, and BC corresponds to YZ. So I'm looking at the ratio between BC and YZ. Well, BC to YZ is 3 to 6, and that simplifies to 1 to 2, okay? So when we're calling the scale factor, we call this K, okay? Now k is equal to ab over xy, which is equal to ac over xz and bc over yz. Again, that's just because these guys are proportional, which when we simplify it out equals 1 to 2. Now this is again comparing my smaller triangle to my bigger triangle. Scale factor works in two different ways though. This is the tricky part. Is my scale factor can also represent what happens if I'm comparing big, the top, to small, the bottom. Again, big to small to big to small, right? Those are two different comparisons, and we can actually do it that way, right? When we're comparing, it doesn't necessarily go smallest to least order, right? When we're actually doing a comparison, it can be any order that we're really looking at, okay? So in this example, right, we could have two possibilities. Our scale factor could be 1/2, or our scale factor could be 2, right? It's all kind of the same idea. Right? If we're comparing x to y, or note that if we're ever comparing some x to y, so something to something, right, we would always write it as x over y. So x to y means x over y. Right? That's why it's small to big means small triangle over big triangle. So if I'm comparing small to big, I should always assume to get a fraction less than 1. If I'm comparing big to small, I should always imagine to get a fraction or a number greater than 1. Interesting how that works. All right, so here we have another practice problem, and we want to, Sheila wants a larger picture of her 8x10 selfie. So here's her 8x10 selfie. Office Depot says that she can only get it in one of two sizes. She can get it in 12x14, or she can get it in 12x15. So which size of those two will keep her picture the same quality with no distortion? So this is kind of the goal, is to get the exact same proportion, but again, if we distort it a little bit or change, if we don't keep it similar, right, we might get something that looks this distorted, or it could look like this distorted. Okay, so we have to be really careful, and so this is just one of those places where understanding similarity really helps. Right, and the solution is, all right, we want to check the proportion of the sides. All right, and a lot of you probably went, well, 8 to 10, right? You went 8 to 10. Does it equal 12 to 15 or 12 to 14? Unfortunately, that's not how we do it. Which side is smaller? 8. Which side is bigger? 10. Which side is smaller? 12 or 14? Which side is smaller? 12 or 15? So you actually have to compare the same side. So this we would be comparing 8 to 12 and then 10 to 14, as well as 8 to 12 and 10 to 15. So what we're looking at, right? So we have to check both proportions. So we're going 8 to 12, small side to small side. Does it equal the ratio between large size to large side? And I have to do that for both of the pictures. Okay? Simplifying gives us 8 to 12 gives me 2 to 3. 10 to 15 gives me 2 to 3. But this one, for the 12x14, 2 to 3 will actually give me 5 to 7. So it's not true. Right? So the best one that we can use will actually be the 12 to 15. If we use the 12 to 15, right, the similar, we will keep the shape similar, and we'll have no distortion. Okay. Now, really quick, we want to look at the perimeters of the pictures, and I want you to compare the perimeters of the 8x10 to the 12x15. Okay. So we already said before that simplifying these two guys gives us 2 to 3. But now we want to look at, well, if I add up all the sides, so 8, 8, 10, 10, will that equal the same thing as 12, 12, 15, 15? Well, the perimeters, what will that ratio be? Okay. So when we look at the perimeters, we'll notice that 2 times 8 plus 2 times 10 gives me 36. 2 times 10 plus 2 times 15 will give me 54. And when I simplify that out, I end up getting the exact same scale factor. Okay. So that's one of the things that we need to know, is that the not only, right, if I'm dealing with similar polygons, not only are their sides proportional, but their sides and perimeter are also still proportional. Okay, and so now we want to think about area. Okay, and area, this is just kind of food for thought. We won't actually go into this. I want you to try and use, right, the idea of area of a rectangle, right, and compare the two similar polygons and see what you notice. Again, just kind of food for thought. Anyway, thanks guys. Good luck with the assignment today. This is kind of a little bit of intro into similarity.